2 days ago, we talked about the difference between nuclear fission and nuclear fusion. Nuclear fission is a process in whereby one nucleus splits apart into two lighter nuclei. So something heavy becomes two lighter things, and then some neutrons on both sides of the deal as well with some energy that's released. The energy is released as a result of what we call a mass defect, a missing mass, the difference in mass between the reactants and products. Mass disappears and gets converted to energy. Does anybody remember the other definition of mass defect that we used? One that seems to be a bit different, but agrees with the first one, in fact, is the cause of the first one. We talked about the difference in mass between what we start with and what we end with. We also talk about the difference in mass between the nucleus and the nucleons. You guys remember what a nucleon is? What's a nucleon, Emma? Good. The particles within the nucleus, the protons and the neutrons. So if you take the mass of the reactants, it will be greater than the mass of the products. But if you take the mass of the protons and neutrons within a specific nucleus, it will also be greater than the mass of the nucleus itself. So we can define mass defect in both of those ways. And both of those ways result in an energy that we call the binding energy. Now, yesterday, we did some problems, or we did a problem, I should say, involving finding the energy that's released, A, in a nuclear reaction, and B, we found the energy equivalence of the mass defect in a particular nucleus. We had 3 problems last night for homework involving finding the energy released in a nuclear reaction. What I want to do is question number 2 and 3. Okay, if you can do 2 and 3, then you're certainly going to be able to do question number 1. Because number 2 and 3 just requires you to do the same thing and a little bit more. Requires you to balance as well. Notice real quickly though, question number 1, we're fusing uranium-235 with a neutron, becomes uranium-236 for a brief period of time, just like the example that I gave you in class was, right? But remember the example in class split up into krypton and barium and then 3 neutrons. This one splits up into ZR zirconium, is that it? I don't know, ZR and TE and 3 neutrons and then some energy released as well. We said that there is multiple combinations that could happen, so don't necessarily expect to see the example that I gave you in the book, okay, or sorry, the example that I gave you yesterday that came from the book, and the example that I gave you 2 days as a nuclear fission example. All right, same process that we went through yesterday in determining what the energy that's released in question number 1 is, okay, and the answer, I assume, okay, works out to be 172.9 mega electron volts. Okay, let's take a look now, though, at question 2 and 3. Question 2 and 3 requires, again, number 3 requires us to do the same thing. Number 2 requires us to balance the equation as well. Number 2 says uranium-235 nucleus absorbs a neutron. So it's going to be 235-92 uranium absorbs a neutron. Whoops. Now, that neutron has to go on the left-hand side, but it doesn't matter whether it comes first, before the uranium-235, or after. That makes no difference at all. It just has to be on the left-hand side of the reaction. Uranium-235 absorbs a neutron and then splits into bromine-87 and lanthanum-146 and some neutrons. The question here is, in number 2, how many neutrons are released? Okay, so let's write in this, but let's leave a blank for the neutrons here so that we can determine what coefficient should be there. Is it 3, like it was in the example that we did yesterday with the krypton and barium? Is it 3, like this one here? Or is it 2 or 4, or something even different than 2, 3, or 4? Let's see. All right, we got to see how many protons and neutrons we have on both sides to figure that out. 235 plus 1 is 236 for a mass number on the left-hand side, 92 for a mass number on the right-hand side. Let's take a look at what we have right now for a mass number and an atomic number on the right side. 87 plus 146 plus 1 is equal to what? I think it's 234. Is that right? 234, 92. All right, so what are we missing on the right-hand side? We have 236, 92. We have 234, 92. What are we missing on the right-hand side? Is it 233? 87 plus 146, I think, is 233, and then 1 is 234. So what are we missing on the right-hand side here with 234? We're missing 2 up here, right? Well, how do you get 2 up there? You can't have this. That doesn't make any sense. But what you can have is 2 more neutrons beyond what we already have. So if we have 1 neutron, how many neutrons do we really need to have to balance this? 3. Got to have 3. So it does end up being the same as the number of neutrons in question number 1 and the same as the number of neutrons in the example we did yesterday. Don't think that it always will be, though. Okay? It seems to be usually 3 neutrons, but it can be different. It could be 2, could be 4, so don't automatically assume that it should be 3 neutrons there, okay? Unless it happens to be a reaction that you recognize from before. Okay, now what we got to do is find the energy that's released in that reaction. In order to do that, as we know, Daniel? Okay, good question. Daniel says, why would that be a 3 as opposed to a 2 on the right-hand side? If we looked at the 236 on the left-hand side, right? 235 plus 1 is 236. And then we take away that 3 for just a second. Okay? 87 plus 146 plus 1 neutron is 234, right? So what do we need? Well, we need 2 more. We already have 1 neutron. So we need 2 more neutrons, which is 3 neutrons. Does that make sense? So we don't want to stick a 2 in front there. We stick a 2 in front there, that becomes 235. 92, right? If you have to do a question like this where you have to stick the coefficient in front, then do what we just did, but then check it. Go back and do the addition again to make sure that you did it right. Because that does get a little bit confusing. I know you say you need 2 extra neutrons, so what do? Temptation is to stick a 2 in front. Hey, if that's a multiple choice question, I guarantee you that's an option, a 2 in front there. So just go back and double check it. If we put a 2 in front there instead of a 3, we add things up. Oh, no, wait, it is 235, so we did make a mistake. Okay, that makes sense? All right, so let's go back now and find the energy that's released in this reaction here. You guys know how to do this, right? First of all, we've got to find the mass defect. And to find the mass defect is what results in the energy loss, right? Or the energy given off, I should say. So let's get the mass defect. The mass defect comes from the difference in mass between what we start with and what we finish with. Let's get the mass of what we start with from that table. If this is a question on a test, then this is going to be given to you not in a table like this, but probably in, a page of information, talking about a nuclear power plant somewhere or something, or, the bomb that was dropped on Hiroshima or something. It'll be given to you in some context, buried in a whole bunch of words, but it'll be there. The information you need will be there. The mass of uranium-235 will be there. Now, whether it's there in kilograms or atomic mass units, I don't know. Probably kilograms, okay, which makes it easier than this question. But if it's not, doesn't matter. Okay, just write down the mass of that uranium-235 in whatever units you have. Uranium-235 has a mass from our table of 235.043930. The mass of a neutron, given to us again on that table, 1.008665 atomic mass units. Now, on the right-hand side, the mass of bromine 87 is going to be 86.920 711 atomic mass units. Lanthanum has an atomic mass of, from our table again, 145.925791. And finally, the neutron, well, the neutron has a mass of 1.008665. We already looked that up. But Daniel, this one has 3 neutrons, so we got to multiply that by 3, right? All right, let's go, you guys, over. Let's find, you guys find the green ones this time. You guys find the right-hand side. And you guys on this side find the black ones, the left-hand side, okay? Simon, what is that? 235.872. No, oh yeah, I did actually. Yeah, you're right. You guys were doing the right side, and And the other side was doing the left side. Thank you. 235.872. Let's keep going. .497 after that. Okay, thank you. So there's the mass of the right-hand side, which we would expect to be less than the mass of the left-hand side, right? Because there's got to be mass lost. Probably something less than 1 atomic mass unit lost, but still less than the than the left-hand side. Who has the left-hand side there? Kirsten, you have that? Okay, thank you. 236.052595. Sure enough, the left-hand side is bigger than the right-hand side. We did lose mass as we expected there. All right, now what's next? Look at the mass of both sides. That's not very hard, eh? Really, it's not very hard. What's next? Yep. Let's get the mass defect. And let's do that by subtracting the two. So the mass defect is going to be 236.052595 minus 235.87, and so on. Does anybody have that number? 0.18 0098. Thank you. There's our mass defect. Now, if this masses are given to you in kilograms, which they likely would be on a test, but not necessarily, then we don't have to, then all we have to do is go to our final step of finding the energy. If it's not given to you in kilograms, if it's given to you in atomic mass units like this, then we got to convert it to kilograms. How do we do that? Well, we say that 1 atomic mass unit is 1.66 times 10 to the minus 27 kilograms. That conversion factor is on our data sheet. 0.180098 atomic mass units is equal to X kilograms. Let's find the mass defect now in kilograms. The X goes up by multiplying. This goes up by multiplying. So X ends up being 0.18 times 1.66. What does that equal? Ben? Okay, too fast. Way too fast, man. 2.9896. 268. Thank you. Now that doesn't seem like a lot of mass lost, but remember, that is the mass that's lost in a one single reaction, right? One single nucleus decays, and that's the mass lost. All right, final step, how do you find the energy that's released in that process? The easy part now. Right, E is equal to mc squared, m being the mass defect. So it's 2.9896268 times 10 to the minus 28, that really small amount of mass lost. If we turn around and multiply that by 3 times 10 to the 8 squared, that's a big number. What do we end up getting there? Anybody? Okay, 2.69 times 10 to the minus 11 joules. And that's good as a final answer. That's good. Now, the answer that was expressed in your textbook was in electron volts. So we'll do that conversion to electron volts just in case you need to on an exam. We know that 1 electron volt is 1.6 times 10 to the minus 19 joules. That conversion factor is on our data sheet. X electron volts equals 2.69 times 10 to the minus 11 joules. Okay, we turn around and solve for X here. 2.69 goes up. We divide those two numbers, and I think we probably should get about 167.8 if we do that. All right. How many people got that? All right. Let's spend just a minute reviewing Rutherford's gold foil experiment, and I mean just a minute reviewing that. Remember Thomson's plum pudding model of the atom? Electrons are floating around in a sea of positive charge. Rutherford fires these alpha particles at this screen, or at this really, really thin layer of gold foil. Surrounding that whole thing is this screen that we call a scintillation screen. We find that most of these alpha particles that leave this box here go straight through. Most of them go straight through this gold foil and strike the screen straight across from it. That tells Rutherford and his assistants, the fact that most of them go straight through, Tells them that most of the atom is empty space. Okay, just like our analogy with the football field yesterday, 110 people run across the football field, maybe 100 of them run straight across, tells them that there's not much on the football field to get in the way. Most of the football field is empty. Okay? Now, not all of them go straight through. Some of them do this. They get to the screen or to the gold foil, and they deflect. They go in different directions here. They still go through, but they deflect. Some of them. Most of them don't, but some of them do. That tells them that there's got to be something there pushing them away from the path that they were going. What pushes a positive alpha particle away from its path? Something that's positive. So there's got to be something that's small. It's got to be small because most of the atom is empty space. It's got to be positive. We'll call it a nucleus. A small positive nucleus pushing these alpha particles away from their path. Finally, a few of these alpha particles bounce back and hit the screen back here somewhere. And that told Rutherford and his assistants that something that was small, that something that was positive, had to be heavy. You run across the football field and you run into something that's light in the middle of the football field, you're going to run right through it. You run across the football field and run into something that's heavy in the middle of the field, then you're going to bounce back from it. Okay, these ones bounce back, so that small positive nucleus had to be heavy. Now the model of the atom that we have as a result of this. Here's a small, dense, positively charged nucleus, and you got electrons orbiting around it in circles here. Now Bohr said that Rutherford's model of the atom was good. It just needed to go a little bit further with it. Bohr said that electrons do orbit around the nucleus, but they don't just orbit anywhere they want. They orbit around in very specific levels. So we have electron levels, and each level is characterized by a specific amount of energy. So it's like going around the track. You're running a 400-meter run around the track. You got to stay in your lane. If you're in lane 3, you got to stay in lane 3. Electrons stay in their lane. Electrons stay in their level. They have very specific levels characterized by specific energies. But something that should happen doesn't happen. The electrons, as they orbit around the nucleus, like my keys are orbiting around my hand right now, they should emit EMR. Why should they? Well, because Maxwell said that accelerating charges emit EMR. How are these accelerating? How are these keys accelerating right now? Look to be going at a constant speed to me. What kind of acceleration do they experience? You guys know this. What kind of acceleration do these keys as they go in a circle experience? Centripetal acceleration toward the center. They're accelerating toward the center. They should emit EMR, but they don't. We know they don't because if they did, they would spiral in towards the nucleus, and that doesn't happen. So they accelerate toward the center of the circle. They should emit EMR, but they don't. So it's as if they're not accelerating. They are, but it's as if they're not accelerating. It's as if they're stationary. Finally, we can make electron transitions. We can jump an electron to a higher level, and we do that by absorbing energy. Remember, if I go from the first deck of the Saturdome to the third deck of the Saturdome, I got to have my drink of Red Bull, or I got to have my coffee, or I got to eat my Wheaties in the morning so that I absorb energy to have the energy to go to a higher level. Usually, that energy is in the form of EMR, but not always. Okay, it could get its energy some other way, but usually it's in the form of electromagnetic radiation. Usually it absorbs a photon, but not always. Has to absorb energy of some type, though. Now, electrons can also fall to a lower level. When they fall to a lower level, they give off energy. They emit energy. And usually that energy that they emit is also going to be in the form of EMR. Usually going to be visible light, infrared, or ultraviolet. Occasionally maybe an X-ray, but usually it's going to be one of those three: infrared, visible light, ultraviolet. Now, the last thing that I showed you yesterday was this, with these pictures here of basically spectra that result from transitions of electrons. First one actually didn't result from transitions. That was just our reference diagram. When you have this solid this liquid or this gas under a high pressure, what happens? Well, it produces light. It produces all colors of light, all the colors of the rainbow. Those colors of the rainbow look like white light. Like when we look up in the sky, we don't see a rainbow normally. We see what we call white light. But when we put that white light through a prism or a diffraction grating, then it splits that white light up into Roy G. Biv. And it splits it up because it's all the colors of the rainbow into a continuous spectrum, literally a rainbow. Nothing to do with atomic transitions up here. Okay, this is just our reference diagram. This is what happens to light that comes from a hot, solid, liquid, or gas under a high pressure. Now, if I have a gas, a hot gas, under low pressure, what's going to happen? Well, it's also going to produce light. It produces light as a result, this time, of atomic transitions, electrons falling to lower levels, from the 5th to the 3rd level, from the 2nd to the 1st level. As these electrons fall to lower levels, each of the transition results in a photon being emitted. So what you see in here in the emission spectrum is a dark background with bright spots on it. The bright spots corresponding to the photons that were ejected as a result of certain transitions. This was the photon that was ejected in one transition. This was the photon that was ejected in another transition, and so on. We get what we call an emission spectrum. Sometimes we call it a line spectrum. Finally, in the third one, we have pretty much the same thing as we have in the first one, our reference diagram. We have this solid, liquid, or gas under high pressure, hot. It emits all the colors of the rainbow, and in fact, that's almost what we see over here, is all the colors of the rainbow. But because we've introduced this cold gas here, some of that light, a few of those photons will be absorbed by the cold gas, and electrons will jump to higher levels as a result of that. As they do that, you start missing some things. You have the continuous spectrum, but now you're missing a photon that was absorbed. This dark spot corresponds to that red light, that red photon that was absorbed, causing the electron to make a certain transition. This yellow photon that's gone was absorbed by an electron as it made a transition from a low level to a high level, and so on. Notice these lines correspond to the lines on the emission spectrum as well. That means that whatever hot gas is producing this emission spectrum is chemically identical to this cold gas that is producing the absorption spectrum. Remember? Yesterday we identified an unknown gas based on these three, and I don't think you guys had any trouble with it. Basically, you got to look at the unknown gas, compare it against the other spectra for gases, and recognize that all of the lines, say for sodium, have to be there in the unknown gas mixture in order for sodium to be there. Okay, make sense? Okay, today we're going to talk about the energies of these transitions, and it's not very hard, so that's the good news here. The energies of the transitions. Take a quick look at this for a second. Okay, let's look at helium because it's kind of in the middle there, and it's got a lot of lines there too. This was on a diploma exam. Now it'd be in color, as opposed to in black and white like this. This was actually a question from a diploma exam, but it was before the days where they would put color on the diploma exam. That would make it a little bit easier because you'd see that this is in wavelength. Okay, the further to your right that you go, the higher the wavelength. That means the lower the frequency. This might be red. This might be blue or violet down here. Maybe you got green somewhere in between. Higher wavelength. Now remember, each of these lines corresponds to a photon that's been emitted by this hot gas under low pressure. In other words, an electron makes a transition from a high level to a low level in this hot gas under low pressure, and it ejects either the blue photon or the red photon or whatever. Quick question for you. How would you find the energy? How would you find the energy of that photon, this photon, or this photon that was ejected? You know what? Here's a question for you before that. Don't answer that first question yet. Which photon is more energetic? Which photon is more energetic? Let's get rid of the colors here so you're not given a clue by that. Which photon is more energetic? Photon 1, photon 2, or photon 3? Which one's the most energetic one? 1 is the most energetic? How come? Good. Yep. E is equal to h c over lambda. E is also equal to h times f. If you have a shorter wavelength, there is a higher energy. Okay? That means that that would also be the higher frequency. So if you're asked a question where you say, which one is the most energetic? Well, then it's going to be the first one. But be careful. Okay, if it's given to you in terms of frequency instead of wavelength, then you got to think the other way around, right? Shorter wavelength, higher energy, more energetic. Now, let's go back to that first question. How would you find the energy of one of these photons? I kind of just gave it away, actually. Take the wavelength of, what, 4.4 or 4.5 times 10 to the minus 7 meters, and use hc over lambda. So there's one way, if you're given an atomic spectrum like this, one way to find the energy of the transition, the energy that's given off as an electron falls to a lower level, is to do what we just did. They just use A is equal to hc over lambda. Now, sometimes we get a diagram like this. Sometimes we get a picture like this. This is called an electron level diagram. This one gives us the energy of each of the levels. Not the energy of the transitions, but the energy of the levels. Okay, don't worry about these words on the bottom. Okay, it just names the series, okay, of the transitions. Notice in this diagram, we can have a transition from level 2 to level 1, level 5 to level 1, okay, level 4 to level 2, level 6 to level 3, and so on. There's almost an infinite number of transitions that can take place. Each of these transitions would correspond to a photon being ejected. Each of these transitions would correspond to a bright line on that line emission spectrum. Now, when you had this diagram, it was easy to find the energy of the transition. You were given the wavelength of the transition. All you had to do is use E is equal to hc over lambda. This time, you're not given the wavelength of the transition or the energy of the transition. You're given the energy of each level. So how do you find the energy of the transition now? Well, the good news is it's even easier, although it may seem harder right now. Let's find the energy of the transition from the 4th level to the 2nd level. This one right here. What's the energy of that photon that's ejected? Well, it's going to be negative 3.4 electron volts minus negative 0.85 electron volts. In other words, it's the final energy minus the initial energy. The energy of a transition is never the numbers that you see on the left-hand side. It's always a difference between those numbers. That gives me negative 2.55 electron volts. That's the energy of that transition. 2.55 electron volts is the energy of the photon that's ejected in that case. Does that make sense? That's not very hard. How would we find the frequency of that photon? How would you find the frequency of that photon that's ejected? I'll give you a hint. It's easy. Yep. Yeah. Well, yeah, you're looking for frequency, so we'd set it equal to that energy equal to h times f, not hc over lambda. But if you're looking for the wavelength, then hc over lambda would be exactly what you said, yes. I know what you mean there. Okay. Don't set 3.4 equal to h times f. Don't set 0.85 equal to h times f. Set the difference between them equal to h times f, because the difference between them is the energy of the transition, and the difference between them provides us with the energy of the photon that's ejected or absorbed. Does that make sense? What if you're going the other way? What if I said a photon with a energy of 10.2 electron volts was absorbed by an electron in the 1st level. So here's an electron in the 1st level, right here. It absorbs 10.2 electron volts. Where's it going to go? So there's a photon of 10.2 electron volts that's absorbed by this electron. Where's the electron going to go? The first level is negative 13.6. You know what? One more little thing, actually. Notice the first level, negative 13.6, they're all negative values, right? And they all get smaller as you get closer. Does that make sense? Well, on one level, it probably shouldn't make sense. Why are these numbers getting smaller? And why are they negative values? It's kind of like this. Right now, our gravitational potential energy relative to the surface of the Earth is 0, right? You climb a ladder, it gets bigger, right? If you dig a hole, but you still measure the potential energy relative to the surface. You dig a hole and you climb down that hole. The further you get down that hole, closer to the core of the Earth, closer to the center of the Earth, the bigger your potential energy becomes, but the more negative it becomes, right? That's kind of what happens here. In the bottom level down here, the first level, this would be the nucleus down here. The first energy level, the second energy level, the third energy level, when the electron is gone out of the atom here, it's ionized. Okay? We define that as 0 energy. So what we do is dig a hole, get closer and closer and closer to the nucleus, it gets more and more negative. All right, so back to my question. You absorb 10.2 electron volts, okay, from the first level. Where does the electron go? Well, if it gives off energy, it's going down. If it absorbs energy, it's jumping to a higher level. Where does it jump to if it absorbs 10.2 electron volts? Second level, right? 13.6 plus 10.2 gives me 3.4. So if I absorb a photon of 10.2 electron volts, then I go to 3.4. Does that make sense? Here's one for you. What if I absorb 10.8 electron volts? Maybe it's not even coming from a photon. Let's not worry about where it's coming from right now. We absorb 10.8 electron volts. Where is this electron going from the first level? Does it have enough to get to the third level? 13.6 plus 10.8 gives me 2.8. Does it have enough to get to the third level? Simon? No. So where's it going? Can't go in between because it's got to be, remember, Bohr said it's got to be on this level or this level. If it can't go to the third level, where's it going? Second level. Right? If we absorb 10.2, we're going to the second level. If there's 10.8 available, what happens? Well, it still doesn't absorb 10.8. It only absorbs 10.2. The other energy just whatever. It absorbs 10.2 and goes to the second level. It can absorb less than is given to it, but it can't absorb more than is given to it. Does that make sense? You guys feel okay with that? I mean, that's essentially it. That's essentially the mathematics that's involved in this. And it's not very hard, okay? Remember, if you see something like this, easy. The energy of the transition is just hc over lambda. The wavelength of the transition already given to us. The frequency of the transition, well, we could say v is equal to f times lambda to find the frequency of the transition. If you're given something that looks like this, you got to always subtract. Always subtract. They never use one of these energies for the energy of the transition. Use the difference in energy for the energy of the transition. And then set it equal to hf or hc over lambda. Is that okay? That's the last bit of mathematics that we have in Physics 30. Nice way to end, hey, with that.